In this video, I show how I built the second half of my 48 volt 24 amp hour lithium-ion electric bicycle battery pack. The first pack cost about $80 to make about a year ago, but it's made of really nice Panasonic cells. Now this pack cost about $55 to make. It's made out of cheapy Chinese cells, but it works really nicely, and I'm very happy with it. If my tests are correct, both of these batteries combined, which is 1.2 kilowatt hours of capacity, will give me over 150 miles of range if I stay below 12 miles an hour. And of course, the faster I go, the shorter range I get. If you have any questions about this project, please feel free to ask them in the comment section below. But chances are, your question has already been answered in one of my other videos. So I would highly recommend, before you asking a question, you go watch one of my other videos about this project, because I've made probably like 20 or 30 videos about my electric bicycle, dating back to when I was first tinkering with the idea for it. So there's a good chance that any question you may have has already been answered by me. Well, anyway, let's see how I made this. Well, look what came in the mail. Laptop batteries, I think. Now I can finally build the other half of my bicycle battery, and I can start using my bicycle again. That's so awesome. They're not name brand, they're just generic. But oh well. The last ones that I got have actually stayed pretty good. The last generic ones that I got, I made a video about them a couple months ago, and they seem to be pretty good. They're only about 2.2 amp hours, but oh well. Let's clean these up and test the capacity of them. So these are held together with a lot of tape, so just scissors will help. .9 volts, that's really good. 1.3 volts, that's okay. 3.09 volts, that's wonderful. 3.09 volts, that's wonderful also. This one that's at 0.3 volts probably will revive okay, but we'll do a discharge test to know exactly how much capacity it has left. Okie dokie, so we're going to be using the IMAX B6 to calculate how much capacity these batteries have. But first we have to get them up to 3.6 volts. So I'm going to use these little neodymium magnets. This is the pack that's at 0.3 volts. And then we'll bring up the power. It's not taking very much power to rise up. These have probably been sitting for like 5 or 6 years in a warehouse. Or they're resistive. Don't know. In that short amount of time of them charging, if I take it back down, they probably go down to like 0.7 volts. Or like that, 0.8. Nice. If I'm putting 1 amp into these two cells, that's only 500 milliamps per cell. So that's pretty good. It is a bit risky to put 1 amp when they're this low though. So I started out with the bottom two cells that were at 0.3 volts, and I got them to 2.2 volts, the same voltage as these two ones. Then I added them together, because they're at the same voltage then, and I'm charging all 4 at the same time. Well, now they're at like 2.9 volts. It's close enough to these ones, so I'll add these ones to it, so they're all the same voltage, and then I'll be charging 6 batteries at the same time. Oops. So now all 6 cells are together, held together with magnets, and we'll charge them at the same time. That'll be a lot quicker. I'll stop them at 3.6 volts. In the meantime, since this is going to take about 20 minutes, I'll go ahead and start ripping open the other packs. So all these batteries have been put up to 3.6 volts. I got all these ones done. Quite a bit of batteries. Now, I did write down what the original voltages were, because I've noticed that even though something at 0.3 volts can be revived, sometimes they can be less stable. So I'm going to categorize all the ones that have stayed at a higher voltage in their own pack, and I'll put all the ones that have been in lower voltage and are thus lower quality into their own pack, so in case they die, they only kill other low quality cells. Now let's charge this one with my IMAX B6 battery charger. Go to 4 amps. And the capacity should start counting up there, as you can see. We'll let that sit for an hour or so and see where it goes. So I've done a few tests, and I've also ripped apart the other batteries. This is the pile of batteries that I've only written down their voltage that they are at right now. And this is the 6 batteries that I have revived and calculated their capacity. And unfortunately, these batteries have about half their capacity that I would expect. Like, I would expect this battery to have like 2.5 amp hours, but it only has 1.4. These seem to have between 1.1 and 1.5 amp hours. That's not very good, but I did get these for dirt cheap, and hey, I finally got purple cells, which is awesome. It kind of helps to fill out my color collection. So far, I've only had 2 short out on me, and these were kind of discolored. Like right there, you can see a band around there. That's where like some electrolyte has leaked behind the plastic coating. To signify that they're broken, I put a circle of marker around it, like that. And now these will go into my collection of dead cells. It's kind of interesting that so far, with like the couple hundred cells I've gone through, I've only found 7 bad cells. Because lithium cells are very durable, and even if they do get very old and used, they still have some capacity in them most of the time. Like, a lot of these ones still have at least like maybe 200 milliamp hours or so, and so if I put them all together, they'd still have a lot of power in them. They might be a little bit unstable from being really old, but oh well. It's been about a week now, and this whole process is going along quite nicely. These are all the cells that I've calculated the capacities on. These are the cells that I haven't changed yet, but they're still at their original voltages. But it looks like a lot of them are at a nice voltage, like 3.2 volts or whatever. These are the ones I've gotten to 3.6 volts, and I'm slowly charging them up to 4.2 and calculating their capacity. And I've only come across 6 bad cells, but I'm going to check those several times, because in case like there's gunk on the terminals, and maybe they're not really bad, and I just like maybe they didn't make a good connection, so they look like they were bad. And very good news about the cells. I forgot that 3.6 volts wasn't 0%, because the only reason I get them to 3.6 volts is because I started doing that, and that's just kind of what I want. I want to keep all the ratings on my cells the same. Like, for instance, the ones I did a long time ago, I want to make sure that these are kind of the same rating. So I just kind of always test them. I always get them to 3.6 volts and test them, test their capacity. Well, actually, you could technically take them below 3.6 volts. Like I took this 1.2 amp hour cell, and I hooked it up to the IMAX B6, and I discharged it, and actually gave 1.7 amp hours, because 3.6 volts. Let's say this is 0% and this is 100% charge. 3.6 volts is actually, after it's already been it's already 25% charged. So that means that each one of these batteries have an extra quarter of their capacity that I wrote down, which I knew that before, but I kind of forgot, and it was just that's why whenever I was adding all these together, and I was thinking, oh no, these cells, they're half capacity. I'm gonna have to have a bunch of them even to make one battery. I might not be able to finish my bicycle battery. Well, actually, this is really good, because if I took these and I made a 24 amp hour, or if I put enough cells together to where these numbers added up to 24 amp hours, well, I would actually end up with like a 34 amp hour pack, because these numbers are actually only 3/4 of their actual capacity. But my other battery pack is actually tested for 24 amp hours, so your battery is only as strong as your weakest link, and that would be the weakest link then. Well, that means that I can make this pack with only 17 amp hours, or 17 amp hours from these labels and from these numbers, and it would actually be 24 amp hours, which is pretty awesome. This means that I could actually get a good majority of my pack done with these cells that I bought, and I could just use some of these old ones to fudge together the rest of the pack, and I wouldn't have to have a huge pack like I thought I would, because I was thinking these cells are pretty bad quality, but actually they're not that bad. I think I have enough cells made up. I need about like 72 cells. I have 55 here, and I have 18 cells here. I was going to use these to make a have a 12 volt 15 amp hour battery pack, but I don't really need that compared to my bicycle, so I'll take these, and I can always put other cells in here. So that should leave me with maybe needing only like 5 or 6 cells afterwards, but that's if saying all these cells are good. So I've charged all these batteries up to 4.2 volts. Now I'm going to go back through and test them. If they are if they're between 4.18 and 4.21 volts, then they're good. But some of them might have a resistive short in there, meaning that they're wasting energy as heat. So if they're anything below at like 1 volt or 2 volt, well then they're bad, so I have to use them for something else. A good majority of the cells were pretty good. I think the other ones that were at low voltages were just because I forgot to charge them. Like this was at 3.28 volts before, it was still at 3.28 volts. So it looks like I just never charged it. I forgot to charge it. These other ones, though, they do seem to have a pretty high rate of self-discharge, which is unfortunate, but that's what you get for having poor quality cells. Oh well. Now what I did was I segregated them into piles relative to what voltage they were found at. Like this is the pile that they were at below 1 volt. This is they were at 2 volts, above 1 volt, and at 3 volts or above. See, these ones that were at below 1 volt, they have a higher chance of being unstable. So what I'm going to do is whenever I have the parallel packs, I'll put all the unstable ones into its own parallel pack. It'll still have the same chance of them dying, but if they did die, they would just kill other unstable cells. They wouldn't kill the better cells, which I think is a pretty good idea. So now let's put these together into the 17 amp hour packs that we need. Now 17 amp hours by the number on here. Now whenever I actually test them, they should be 24 amp hours. So let's see what we can get and add the numbers together. Well, I believe I have all the cells I'll need to build the 24 volt, 24 amp hour battery pack. I have 6 packs made up. 1, 2, 3, 4, 5, 6. Or at least the cells grouped together to make the 6 packs. Should be 4 volts, 24 amp hours per pack. Then when I hook those together, should be 24 volts, 24 amp hours. First off, we're going to connect all the cells together. So we'll have 6 packs held together with duct tape. Then I'll use my big soldering iron to connect all the cells together. So we have all the cells in parallel for each pack. Then I'll probably test them a little bit. We'll hook them all together, connect them in series, and then we should have a 24 volt, 24 amp hour battery pack. And all we have to do is add the balance leads, which shouldn't be very hard. Just a 9-pin D-sub connector and a couple of wires. Well, it seems like I can't really use only duct tape for these individual cells or even these ones because, see, they slide around inside of them. I forgot that the last battery I made was made with cells in packs of 4, so they're just kind of locked together like Legos. But these ones move around too much, and so it's kind of floppy. So I'm going to get out my hot glue gun and just glue them together. I haven't used hot glue in years, but I think it'd probably be the best thing. It'd be, because I don't really need anything strong. I just need something to hold it in place while I duct tape it. Oh, look at that. Isn't that wonderful? Sturdy enough. Pretty cool. That hot glue worked pretty nicely. I'm very happy with it. I might start using hot glue for stuff more often, especially batteries. Now what we're going to be doing is I'm going to be putting another layer of duct tape around each parallel pack, that way they're a little stronger. And then I'm going to be hooking all of these together with duct tape. Now these ones have the same amount of cells in the parallel pack, so I'll put a couple bands of duct tape around here. And I have this one which has a little bit more cells in it. Put a layer of duct tape around it, take this one, another layer of duct tape, take this one, and another layer of duct tape. And I think that'd be a lot sturdier than if I just put duct tape around this whole thing, because if I did that, this bigger side would make it to where the duct tape wouldn't stick on the inside. Well, that turned out wonderfully. I'm very happy that this battery didn't turn out nearly as big as I thought it would be. This is a battery I made a year ago, which should have the exact same capacity as this one. See, I was expecting that these batteries would be such low quality that I have to have a bunch of them, like it'd be like this wide or whatever, and it'd be huge. But I'm going to be able to fit both of these. I could probably actually fit like 6 of these into the battery box of my bike. And if I just fit these two in there, I'd still have plenty of room to put mail or rocks or stuff I buy at yard sales or whatever in the back of my battery box. Pretty awesome. Now let's take some of this wire and connect these cells together so it actually functions as a 24 volt 24 amp hour battery. And I'll just got to warm up my soldering iron, then we can do that. I think the soldering turned out pretty nicely, at least functional. The packs are connected up where it snakes through like that. So this is negative and this is positive. So now that we have the basic structure of the battery assembled, we're going to have to be able to use the power. So I'm going to have to add some wires. I'll have a positive wire coming off and a negative wire coming off, then 7 other wires coming out for balance charging. I'll do it exactly the same way that I did my battery a year ago. I'll have the 2 green wires coming out. These are 12 gauge copper wire. And then I'll have these other wires, which I think are like 16 or 18 gauge wire. These are for balancing, going to a 9-pin D-sub connector on the end. See, these actually connect up into my little adapter I made from my battery charger. I have the same spools as I used before. I have the 12 gauge copper wire that'll come off the negative and come off the positive to power the motor. Then I have this reel of like 1950s or 1960s telephone wire, or I don't know what kind of wire it is, but it's 4-pin, so I'll use 2 strands of this, probably about 1.5 feet or so each, and they'll go from each connector on the battery to this 9-pin D-sub connector. Unfortunately, I was kind of in a rush, so I accidentally got the solder-on type. I've only been using the crimp-on type, but we'll see how this goes. If not, I can always run back and get the crimp-on type. So there seems to be a lot of confusion about how balance wires should be connected. Well, on your IMXB6, there's a negative and a positive. Well, that goes from 0, 4, 8, 12, 16, 20, 24 volts. Well, pretty much. Well, of course, if you're charging to 4.2 volts, it'd be 4.2, 8.4, 12.6, whatever. But I'll just say 4. So I have the 7 wires for a 6-cell battery. If you had 3 cells, it would be 0. You'd actually have 4 wires. It'd be 0 volts, 4 volts, 8, 12 volts. Well, this is a 6 series battery, and it has 7 wires. So it has 0 on the negative, 4, 8, 12, 16, 20, 24. That's where the 7 wires connect. Well, I kind of wasn't paying much attention to this when I soldered it up, so let's see if I got it right. I'll start off by connecting the pins over here. Should be 4 volts. Yep. 8 volts. Yep. 12. Yep. 16. Yep. 20. Yep. 24. Looks like I did it right. Awesome. So the balance wires are all connected up properly. Now all we have to do is add the little crimp-on connectors for the ends of this. And that's pretty simple. Just take my wire strippers. And there we go. So now that I have the connectors in the end, I can connect the 2 batteries together. So that's what I did. If I connected up wrong, each battery would cancel each other out, so we get like maybe 1 volt at most. But if I connected it right, we should get like 50 volts. Let's see. Awesome. It's working wonderfully. I taped down the wires so they're a little bit more organized. And the IMAX V6 doesn't seem to have any issues with this so far, so let's try to charge it. Wow, look at that. That's all the cells. They're a little bit out of balance, but I'll let it charge. So both battery packs are fully charged and fully balanced. I got them done last night. Now what I think I'm going to do is I'm going to take them for a little test drive because I don't have the plastic that I was going to put on the outside with me. I left the plastic pieces at my dad's house. So instead of having him drive me over there, now that I have the battery done, I'll use the battery to drive me over there. I can grab the piece of plastic and we can finish the battery. I'll put a little bit of this towel around it to help absorb shocks and whatnot and make sure it doesn't get too shaken around. Let's take it for the first test drive. Now I'm going to go on the highway. Probably go about 30 to 35 miles an hour. Now that was a nice little ride. I was able to find the plastic pieces I was needing. No reason to throw them away when I can use them for other projects. Well, we're back at my house now. I'll take all this tape and stuff off this plastic, and I'll put it onto the battery. If there wasn't a cat in the way. And I'll cut around it and then tape it on there. And that should be a nice and sturdy case. And there we go, it's all sealed up. I think it turned out wonderfully. Now what I'm going to do is I'm going to see about charging the batteries and seeing how much energy I spent on that like 4 mile or like 3 or 4 mile ride to my dad's house. So it took 725 milliamp hours to charge this battery. Let's see how much capacity it took to charge this one. Well, it's only gone up about 20 milliamp hours in the past 45 minutes, so I'd say that's good enough. Let's go take it for another spin. This time I'll go 12 miles an hour, or less, instead of the 30 miles an hour like before, and we'll see if that has any effect. Okay, let's go. This trip I'm going to have a little bit of cargo for another project. So it turns out that trip only used 400 milliamp hours. That's almost half the power. So for every mile at 12 miles per hour, my bicycle uses up 120 milliamp hours of capacity, which is a very small amount. That's only 6 watt-hours per mile. I've heard some people that their motors take 45 watt-hours per mile, so this is really efficient and a big battery. So now if we have 120 milliamp hours, you can actually divide the 24,000 milliamp hours that's in these packs by the 120, and we theoretically could go 200 miles on a single charge. I'd say that kind of blows my mind, so I can't believe that math. So I'd say maybe half that, maybe 100 miles, but still 100 miles. I can't believe it, 100 miles. And also about the durability of these. Since the last clip, I've actually put about 80 more miles of distance on these batteries, and they're holding up wonderfully. I have to say, this was a wonderful $50 investment. Even $80 for this one, it's even better because it's made of Panasonic cells and they're a lot more stable and they'll last longer. So I'm really happy about this. This is really awesome. But this video is way too long as it is. It's already over a half hour long. I hope you enjoyed this video and thanks for watching. See ya!